Recording in progress.
Don't I always get to lower the microphone right after I go, right after Gene? That's always the first thing I have to do. What a great conference again. I thank everybody for attending, and thank Gene, Dana, and the team for doing a wonderful job with SERC, with the waste conversion technologies, with the plastics. Wonderful conferences, always amazing panels, as you'll see here, as we've seen for the last couple of days. Even when I get the chance to speak at these events, I always learn more than I teach at these events because they're just great panelists. So I'm very happy to be with all of you, and hope we wind down the conference. And is there good weather out there? I haven't looked out the window yet. It's went out there yesterday. It was quite a storm. But our first presentation today is going to be a comparative analysis of converting non-traditional recyclable materials. It's how three facilities process similar input material. We have Matt Davidson, who is the sales manager with Waste Alternative and Fuel Systems, Vecoplan, LLC. Looking forward to his presentation. Welcome.
Thank you, Steve. Well, ladies and gentlemen, thank you for being here today. I guess the rest of the folks that should be here got blown away yesterday with all the wind, so it's shame on them for stepping out there yesterday, hoping to play golf maybe. But as Steve said, I'm going to give you a crash course in about 20 minutes on taking, for the most part, 3 through 7 bales or 3 through 7 loose material through 3 different processes to create 3 different end products. Those 3 processes will be to pyrolysis, to recyclable material, and to fuel. Once I go through those 3 processes, we'll get a little more in depth with each of the different applications and each of those sortings and shredding and drying and so forth in each of those processes. Just a real brief overview of Vecoplan. We're a German company, started in 1969. We're a shredder manufacturer from way back when, but with shredding, as many of you know, there's integrated systems involved, whether that be conveyors, sorting, storage, in-feed, etc. The office that I am out of is in North Carolina, a little town called Archdale, very close to Greensboro and High Point. We've got roughly 80 employees, and for North America, we've got over 5,000 installations from very simple post-industrial plastics, paper, etc., to very complicated waste-to-fuel systems. We've got a couple more offices in North America, and they're more of a subsidiary of Vecoplan LLC, and that's just to help us with service, parts, etc. throughout North America. We've got one in Indiana, and then another, which is actually a grand opening tomorrow, Vecoplan West in Eastvale, California, so we can give a better product, better service to folks, especially on the West Coast. In North Carolina, we've got extensive parts and service. We've got over $7 million worth of parts. As many of you have probably found out, when you're shredding, you've got a lot of wear items. We've got all of those items in-house. Gearboxes, belt, motors, the list goes on and on. I can go into a ton of detail there, but that's not what this is really about. But for the most part, anything you would need for a system, we have. These are just various locations across the globe, obviously the majority of them in Europe, because they're always 30 years ahead of where we are in terms of recycling and fuel production. But you can kind of see the blanket of Vecoplan over the globe. Now to really the good stuff here. We serve various markets: wood, biomass, paper, document destruction, post-industrial plastics, medical waste. But really, we're getting into, for today, alternative fuels or plastics to a recyclable product. The first process, plastics to pyrolysis, it's the most difficult front-end system to provide because there's more sortation required, or a densified product is required, or a moisture content is required. Sorry for the typo here. You've got pre-shredding and sorting. It should just be pre-shredding first. For the most part, the material comes in bales or loose, but we typically see baled 3 through 7 plastics, just like you see in these photos here. And for this specific system, we had to go all the way through the sortation, all the way through drying and pelletizing, because this customer required a 20 to 25 pound per cubic foot density, so fluff wouldn't get it, and they required below 8% moisture content. And just allowing the material to flow through the system would not provide below 8% moisture content. So we've got all these steps. We're going to go through a flow diagram and kind of get into those in a little more detail. Like I said, 3 through 7 plastics. So you see the left side, that bale is ugly. It's got boat wrap, it's got shrink wrap, it's got grocery bags, buckets, portable chainsaws. It's got all kind of stuff in it, just really ugly stuff. You guys have seen this, I'm sure, in many of your applications and comings and goings. The final product, like I said, was a plastic pellet, which you see on the right-hand side. A very brief flow diagram, so just using 10 tons an hour as an easy number to take a look at. We've done various 5, 10, 15s, 24s, 6s, you name it. So we start with the pre-shredder. Bale goes directly into the pre-shredder. We try to bring everything down to 8-inch minus. That way, anything that's inside of a bottle, anything, we're trying to cut everything open, liberate anything that might be hiding inside that bale. First step after that will be an overbelt magnet to remove the wire from the bale that has now been liberated, and any other uglies, like I said, the chainsaw, the brake disc, all those kinds of things, we're going to pull that out there. Then an eddy current for aluminum. A lot of our customers find there is still a significant amount of aluminum cans in some of those bales that's worth recovering. An eddy current will remove some other non-ferrous. It's just not quite as efficient. So it's really an aluminum removal tool. We do see some low-grade stainless and maybe some copper get ejected there as well. For this particular application, they needed PVC removal for emissions reasons. Now, I'm sure many of you understand that when it comes to a chemical or a burn process, PVC is a no-no. So we have a step to remove that. And all of these removal rates are just rough estimates of what those material types coming in reflect. The next item being reshredding. Most of the time the customer dictates to us their final reshred, whether that's 1-inch minus, 2-inch minus, 3-inch minus. In this scenario, we dictated the reshred size because we had to pelletize. And that pellet unit required a specific shred size. And in this case, we were about 1 1/4 inch reshred. Then we just go through a simple rotary drum magnet, try to clean up a little more of those metals, the small stuff, shavings, paper clips, staples, all those things that the first pass didn't get. Next step, dryer. This is dictated, one, by the customer. They required below 8%. We couldn't guarantee that just flowing through the system. And the pellet units. Any moisture left in that material, when it creates a pellet, it's going to make heat. That moisture can then turn into steam and pop open that pellet and degrade that material. So we want to keep that pellet hard and fast. So that's sort of twofold there for the dryer requirement. After that, we went to a simple storage system and then onto their pyrolysis unit. Process 2, plastics to recyclable material. Flow diagram is going to look extremely similar. There's just a few things missing off the end. This particular application, 3 through 7 bales, a little bit cleaner, mostly rigids. So laundry detergent bottles, buckets, that sort of scenario. They required a regrind down to 3/4 inch because they create various low-end plastic packaging components, whether that's corner pieces for pallets, sheets to separate materials in pallets, simple structural plastics inside of TV boxes, that kind of thing. So they have a truly recycled end product. With that, same scenario, pre-shred, overbelt magnet, eddy current, you kind of get in the theme here. Unfortunately, there's a typo here. The PVC removal for this system was PET removal. They were finding some PET in the bales that the MRF didn't catch very well. So they decided to eject it because it made sense for them to send that to a pure PET recycler because it's a more lucrative outlet for it. The rest were 3 through 7s, just a myriad of plastics that they could create these simple plastic products from for packaging and things of that nature. Reshred, rotary drum magnet. You see there's no drying and no pelletizing. This material went straight to a wash line. They would wash the material and then create their end product. So you see it got a little bit simpler. Same scenario, same pieces of equipment, same material coming in for the most part. A little bit different at the very end of the line because of that end product being a little bit simpler to provide. Plastics to fuel is probably one of the simpler to do because for the most part we're talking about cement kilns, maybe cogen boilers, and they have a lot of back-end emissions control already, scrubbers and things of that nature. You guys understand most of that. So it's going to get a little bit simpler, but it's going to be very similar to the recyclable material. This scenario, it came in loose. So we had styrofoam, packaging, wood, cardboard, you name it. This this system in particular provided a briquette to a cement kiln. They wanted one that would ship a little bit better, give them a little better weight, and the cement kiln required it for their in particular feed unit. They needed that density to be a little higher for efficiency. You see the exact same scenario as you saw just before, but this actually is proper PVC removal for emissions reasons. They have emissions control on the backside, but we were able to give them some cheap insurance, we'll call it, by removing some of the PVC to give their emission system a little bit easier approach. Also, pre-shred overbelt, eddy current, reshred, rotary drum magnet, and we loaded trucks directly and they shipped it away to the cement kiln. I have blown through 3 systems just very, very quickly. We're going to get a little more in depth in each one of those processes now so you can see it a little better instead of just this 30,000 foot look at it. We always start with pre-shredding, so a bale will go directly into a pre-shredder, kind of like what you see here on the left, and on the right, that's actually a 6-inch screen producing that material. So you'll get some film bags that come out at 12 inches long, but for the most part, any rigids are going to come out 6-inch minus, and that gives us the opportunity to really separate material well. Understanding what comes out of that shredder, knowing how to size the sorting equipment appropriately beyond that is really crucial for these style systems. So here you're going to see, very simply, a bale is going to be coming over the top. It's going to go into this shredder, and you're going to get an idea of what's going to come out underneath. For the most part, everybody sends them in with the wires, especially at 10, 12, 14, 20 tons an hour. To remove those wires, it becomes very difficult. So we remove the wires in the pre-shred. This particular application has an 8-inch screen, maybe a 6-inch screen, but here in a minute you'll see the ram is going to go forward inside the shredder and it's going to really start pumping material out. And the next video that I'm kind of bump to is you're going to really see the material coming out. So you see the films, they come out a little bit larger. The ridges are going to come out a little bit smaller, but everything's going to be opened up. So anything hiding inside of a plastic bag, inside of a laundry detergent bottle, we're going to be able to pull it out. Metals, PVC, papers, if that's a requirement or otherwise. This is around 6 tons an hour for this system, I believe. So you see the liberation. So we've gone through the pre-shredding, throw the bale directly in. The next step we always want to do is the metal separation. This overbelt magnet is going to pull out the wires that we've now liberated from the bale, and also the brake disc, the hammers, screwdrivers, all those crazy objects. And you kind of see on the right-hand side, that's roughly how large the wire will come out. And you'll start to see some of the wire being pulled away. There was a few pieces there. So that is really crucial for the reshredding and for the final product. But really, even if the customer said, I don't care about the metal, we're going to remove it because we don't want to put those kind of things into a reshredder. The non-FE metal, like I said, an eddy current, is going to do a really good job at aluminum, which you'll see here. Once again, the pre-shredded material really gives a good efficiency for separation because everything's a smaller particle size, typically 2D. We can really spread it across, and you're going to get a really good efficiency out of that eddy current. You'll see some of it being ejected here, some of those aluminum pieces. And these were supposed to be clean 3 through 7 bales, and you see, in an hour, you can really fill up a Gaylord box from what's supposed to be bales that have no aluminum in them. And as most of you know, an eddy current can remove some coppers, some low-grade stainlesses, but really, if somebody asks me, it's going to remove aluminum, and everything else is just going to be a byproduct of what it removes. The PVC removal, for some cases, some of you may be creating a fuel for cogen boiler or pyrolysis, etc. This is a natural requirement. This is PVC removal from 3 through 7 bales, again, that had a lot of film in it. One of those first bales you saw that had a lot of film kind of hanging off of it. PVC is becoming more and more prevalent in a lot of material that we see. Water bottle labels can have PVC in it. It's surprising how much PVC is kind of creeping into some of these other products. So you saw some of the ejection rate there. It's a little more than what some people expect. If somebody came to me and said, if I'm getting a 3 through 7 bale, how much PVC might be in it? I'd say expect around 5% is a good place to start because we're seeing that. This installation in particular and the other one where you saw the bale going in, They're also getting some PVC. They're creating a recyclable material, so they don't care about the PVC. It works for them. But for these folks, they had to have it removed at a very high efficiency and get it below a certain threshold. So we're seeing PVC creep more and more into these products. So just keep that in mind, because the folks they were buying material from said, oh, PVC is going to be really low. We do a good job at pulling it out on the front end. Me and you can see a piece of PVC pipe. We see that plastic outdoor furniture. We know it's PVC, but PVC is showing up in a lot of other materials that me and you can't recognize. So trying to pull it out manually is becoming more and more difficult. The reshredding process, for the most part, is pretty simple. We're taking big pieces, making them really small pieces. In this scenario, you've got roughly that 1 inch minus material coming out here, and this is roughly 8 tons an hour. You see some of that steam coming out of the reshredder, so there will be some moisture driven off through that shred process because there's some heat involved, but we never use that as a drying method because it's very difficult to quantify that across the board because that's not what it's meant for. It is a byproduct and it can be helpful, but if you really require a specific moisture content, that's where you're going to get into drying. Here's a very simple picture. On the right, large pieces. On the left, small pieces. That is reshredding in a nutshell. As I was talking about drying, here's a couple different methods of drying. Based on throughput, you will go one way or the other. The one on the left is a vibratory fluidized bed dryer. So it's think of a hockey table with the air being pushed through it. This one just happens to be a hockey table that vibrates and moves material in one direction, and warm air is pulled through. So you're going to vibrate that material, keep it moving, and it's just a function of residence time inside of that temperature to remove that moisture. We typically don't want to dry much higher than 150, 160 degrees Fahrenheit because we don't want to melt anything. The rotary drum dryer would be for typically larger throughputs. The one you see there on the right is one we installed. It's 40 tons an hour, 30% moisture content down to 10% moisture content, and that was an MSW application. The next couple spots here, you're going to see sort of inside a vibratory fluidized bed dryer. So once again, wet material going in at the far side, dry material coming out on the near side, and it's just a function of residence time. It's not anything crazy going on. It's just how much moisture you got coming in, how much material do you have coming in, what's the moisture content required going out. They figure out how much time it's got to stay inside that heat. Same thing for a rotary dryer. This video is going to go in a little more depth so you can see a little more of the inner workings. This was the MSW application. This was a 1.5 inch minus RDF. They're going to show it going into the feeder, so you'll see kind of how moist the material is. It kind of stays together. This was roughly 30%, which is what we typically see out of MSW. The gas fuel train in front of the dryer. And this one is an older dryer. This one's probably installed 20 years ago, so you see that open flame. That's a no-no these days, so just disregard that. You didn't see that. And this is roughly 8 tons an hour. This was a full-scale test that we were able to provide before the 40-ton per hour dryer was installed. It's going to go in, and just like your dryer at home, it's going to tumble, just like your clothes do, but it's going to go down the length of that tube. Once again, it's residence time. Residence time inside that heat, driving off that moisture. One of the byproducts we'll call of this system is there's an elbow there, and air is moving all that material. As soon as it's dry, it'll be captured in that air and sent upward. Anything heavy is going to fall out. So if there's rocks in it, metals, things of that nature, you'll see it here. There's some copper wire, some other rocks and things like that, and it comes out and it's warm to the touch. It's not a burn hazard or anything like that because we do not dry at very high temperatures. And there's your dried material at this test facility. Obviously, there's a lot of dust there. And in a real system, you're going to get a cyclone and bag house to encapsulate all that dust and reintroduce into your system because that's good material you don't want to lose. After you dry, the more complicated systems may need pellets for 20 pounds per cubic foot material. That's sort of this next part of it. You've got 2 pellet units here in the photo on the left. You've got the pellets it created on the right. Once again, this was a 20 to 25 pound per cubic foot bulk density. And what's really good about a pellet is it flows like grain. So it's very simple to put in a silo, truck. There's lots of devices out there that already handle this kind of material, being in the grain industry. So you see it flows very simply. It doesn't really bridge up anything like that. So that's one good thing about it. but it is a maintenance and a capital cost to do this. And it's all going to be based on the economics of what you're trying to create on the back end. If it's a logistic shipping problem, a storage problem, or in this case, the customer's efficiency of their pyrolysis goes through the roof at 20 pounds per cubic foot instead of 6 pounds per cubic foot. So it made economic sense for them as well. After, whether it's an RDF fluff or a pellet scenario, various feed options, whether that's a metered feed or a bulk feed, and storage options, whether that's a simple floor storage with a front end loader or automated storage. So you've got all these scenarios at the back end of the system to feed these fuel systems or these pyrolysis systems or even the recyclable material systems, because that wash line wants to receive 5 tons an hour, where our systems are going to kind of go between 4 and 6 tons an hour, because when the ram goes forward in a shredder, throughput goes up. Ram goes back in a shredder, throughput goes down. So you get this sine wave of material, so we'll provide a metering device for that. The pictures you see here are actually feeding a gasifier. So we fill up roughly a 15-minute bin, and those screw conveyors are meter feeding into those gasifiers at a very specific rate, and they get feedback from that gasifier. Oh, I need a little more, I need a little bit less, and that VFT speeds up or slows down. I've gone extremely quickly through this, trying to be mindful of everyone's time and Dan's time after me. The main thing is understand what you have coming in and what you need going out. And connecting those dots in between the two are going to be solely pushed by those two items, point A and point B. The other piece of this puzzle is all of these customers were bringing in 3 through 7 bales or 3 through 7 loose material. And part of their economic approach was the folks that had this material, whether it be a MRF or a company that's just creating this type of material, they have to pay to have it removed, $30, $40, $50 a ton. They would go to said MRF and say, I'll take it for $20 a ton. So they've got income coming as monetary income as the bales come in, and they've got monetary income as the finished product goes out. So just keep that in mind, because not always do the economics work out when you look at what end product I'm creating. Bringing in that material and having someone pay you to off-take that material at half the price is a win for them and a very good monetary income for the folks that are creating the end product. But thank y'all so much. Hopefully I didn't blow through it too quickly. Obviously, if you got any questions, I'll be hanging around. I've got business cards. I can get to you and we can speak more later. But thank you for your time, and thanks for hanging around and braving the storm yesterday.
Excellent presentation. It's good when we see it put together as Matt has done. It comes down to, for all of our projects, feedstock, process, and offtake. That makes the economics, that makes the project scalable. And the better you are at the 3 of those processes, and as you wrapped up with it, putting the 3 of them together, that's what gets successful projects. So thanks again, Matt. Our next presentation is going to be equally as enlightening, and I know Dan is going to talk about Shell Chemicals and Sustainability. Dan Falla is Technical Service at Polyethylene Films and Shell Polymers. I've met him before and looking forward to hearing him speak.
This is kind of cool. I get to raise the mic. I'm not used to that. Well, that's a good segue into exactly what I'm presenting. So you all know Shell out in the industry is the big signs that you see with gas stations, etc. That's what Shell was. We're reinventing ourselves into a different company. I've been with Shell for a little over 4 years, and prior to that I was with Nova Chemicals, a major polyethylene producer in North America as well. And then previous to that I was with Dow Chemical for 27 years. So I spent my career and my life as a resin producer and working directly with customers. Throughout that entire time, I was always focused on sustainability, how to make it thinner, stronger, cheaper, clearer, that sort of stuff. So taking a trash bag from being 5 or 6 mils down to the 3/4 mil. There was a lot of work that went into redesigning of the polymer systems, and the polymers being used in that. Multi-layer co-extrusion was really the answer and key to do that. And little do you know, but that salad bag that you buy in the grocery store may contain up to 11 different layers in it, and each and every layer is designed for a specific function, keeping the carbon dioxide in there, allowing oxygen in and out, that sort of stuff. So there's these products, these plastics that are being used today are very much engineered for sustainability and overall reduction in source material being used. That being said, we still need to take on the responsibility of what to do with it when it's at its end of its useful life. So this is a PDF, so I hope this is going to work. Okay, so I want to cover 3 major areas. Why sustainability, our climate targets, and what Shell's approach is. And we're in the process right now of completing the United States' largest single construction site, and that's a polyethylene plant being built up in Monaca, Pennsylvania. The rest of the world would be Monica, but Pennsylvania, it's Monaca. And I've had to learn how to say that. It's northwest of Pittsburgh, and overall it's an ethylene cracker plant, and we're already starting off with sustainability. The frack gas that's coming out of that geographic region is rich in ethane, and ethane is not so good for natural gas for consumers. So previously that ethane would have been taken out of the stream and flared or something else done with it. So we're taking that waste feedstock and then cracking it to ethylene, and then through our reactor system converting it to polyethylene. And we hope that the next phase after that is once we complete the pyrolysis process, as you talked about, using a mass balance concept, we will make polyethylene again from the waste plastic that's coming into the system. So why sustainability? In 2017, the European Union set a target for recycling, and they want 50% recycled by 2025 and 55% by 2030. Major challenge with that is feedstock acquisition. My major role at Shell until our plant is up and operational, and even after that, is I'm the waste plastic feedstock strategy lead, and that's trying to find the waste plastic that we can use for pyrolysis process. Everybody says, hey, there's lots of plastic out there, what's the problem? We can't find it. At least the quality that we need. We need polyethylene, polypropylene, and polystyrene at a competitive price. We don't want the milk jug price. That's just not going to work for us. So we're down in the dirt looking at Murph film and that sort of stuff. China, largest growing area, they have a target of emissions peak by 2030 and then carbon neutral by 2060. Those are pretty lofty goals for a country where the middle class is expanding at an absolute incredible rate. So our climate targets specifically, under the UN Paris Agreement, try to maintain average temperature growth of 1.5 degrees. 1.5 degrees is not very much, and it's really hard to pick what it is. And I've asked this question many times. Are we going in or are we coming out of an ice age? And if you look historically, the Earth has gone through a number of changes with regard to going in and out of ice ages. So we are going to see climate change. We've seen significantly more variations in climate change recently. But this is Shell's target, that by 2050, we're going to be carbon neutral. And we're doing a lot of things, and I'll go over the next few slides and exactly how we're going about to do that. And the absolute target, you can see on the right-hand side. So our sustainability ambition, reduce CO2 intensity, and enabling a circular economy. So with regard to the reducing the CO2 intensity, I'll present some slides that go into it. And it's investing into new materials, new ways of manufacturing. We have a joint venture with Dow Chemical on using a new technology to really reduce the amount of energy required to produce ethylene from methane. And there's a number of carbon capture technologies we're using, more sustainable systems with renewable resources, biofuels, renewable natural gas, as well as waste-derived fuels. On the right-hand side is what I'm really involved in, and that's the circularity, decoupling economic activity from the consumption of finite resources, and I'll go into that as well. So make, offer, and champion. So from the make perspective, energy efficiency, lower carbon resources, in other words, how to more smartly use the energy that we're using to produce chemicals. Shell is really a chemical company, and you may not know it, but a large portion of materials that you use on a day-to-day basis originated from Shell. We're probably one of the largest producers of isopropyl alcohol. I live in Canada as well as Pennsylvania, and the city that I live in, Sarnia, actually has Shell's isopropyl alcohol plant. It was up on the market to be sold, but it's been taken off the market since. So we're a major supplier of chemicals to the industry. MEG, monoethylene glycol, used in a variety of applications. The methanolysis or glycolysis process for molecular recycling of PET. MEG is also used in polyurethane applications. Surfactants from Procter & Gamble, Johnson & Johnson, SC Johnson. There's a lot of surfactants that come out of a variety of the plants that we have. Carbon capture and storage technology. We have an active project up in Western Canada in which we've been able to capture more than 5 million tons of carbon dioxide, and that project is being expanded into other geographic locations. And alternative feedstocks, and that's the renewable natural gas as well as the plastic waste that we'll talk about. Offer circular solutions to our customers. We're being pushed by the brand owners. And what's really interesting, if you look back on where we are today and the big push on recycling, it's different from what it was back the time ago that oil was very high. The whole industry has changed, and a lot of it's been driven by the consumer. The consumer has driven the policymakers are driving the brand owners, and the consumers are driving the brand owners, which is helping to drive us as well. And without that constant push, it probably wouldn't be sustainable in terms of the investment that everybody's making. But with all the changes that are happening, it's here to stay. Like, I'm firmly committed that from my specific responsibilities, and that's to chemically recycle, or advanced recycle as I've been told to call it, 325 kilotons, a little over 800 million pounds by 2025. Those are pretty lofty goals, and we have a very short time frame in order to be able to do that. So Champion, Alliance to End Plastic Waste, we're a very active member with them, as well as partnerships in a number of different organizations. The American Chemical Council, Association of Plastics Recyclers. We had the conference last week up in Washington, D.C., but very active out in the marketplace. So some of the ways that we're initiatives across our global manufacturing sites delivering on our decarbonization. That's reduction in our carbon footprint as well as the capturing. Some specific things, Moerdijk Chemicals in the Netherlands, they've been able to modify their system and reduce emissions of carbon dioxide by about 10%. Shell Polymers US, this is the facility that I'm involved in up in Monaca. We have the most state-of-the-art technology being used. We're a licensee for the polyethylene crackers reactors that we're using, as well as the crackers for the ethylene. So most state-of-the-art, most energy efficient, as well as our rail car fleet system. We have some of the most advanced rail cars out in the marketplace. Really state-of-the-art, and it's kind of fun being at the grounding of this whole brand new business inside of Shell. We were not a polymer producer previously, except for about 20 years ago, 30 years ago, where Shell made polypropylene, and now we're back into the polymer business. And you'll see further announcements of us producing polyethylene around the world. Low carbon energy sources, Reinhold Energy, 1,300 tons of, I can't really read it from this side, tons of hydrogen. Oh, we're also a major hydrogen producer. And we're going to be using that hydrogen for fuel for vehicles as well as for other applications. And that's really taking water, using energy, breaking it apart, and producing hydrogen and oxygen. Alternative feedstocks, Norcor Chemicals. We have a major refinery that's located just outside of New Orleans, and it's a heavy oil cracker, and serendipitously, that is the only reactor, the only heavy oil cracker in existence in North America, where we can take the heavies from the pyrolysis producers as well as the oil industry. It was late in being converted, and fortuitous to us, it turned out that being a heavy oil cracker is a major advantage for the pyrolysis industry. So in pyrolysis, you're taking waste plastics in the lack of oxygen, heating it up, and then breaking it down into a series of different hydrocarbon chain lengths, from very heavy oils all the way up to fairly light gases. And we can take the entire kit and caboodle and put it through the reactor, and it's going to work. And what we'll end up doing with that is using a mass balance approach, so the carbon credits coming out of that will then be credited back up to the Monaca facility to produce a green polyethylene. Carbon capture, I already mentioned about the 5 million metric tons being done up in Canada, and that technology is going to be expanded globally. So this is where I'm involved. So Shell announced that by 2025, we're going to chemically recycle 1 million tons of waste plastic. And that's going to happen in 3 geographic locations: in the Netherlands, United States. Norco is going to be the facility that'll take the oil, as well as Asia Pacific area. So balance that out, it's 325 kilotons here domestically. The one neat thing about Shell that I very much enjoy working for this company, we would rather under-promise and over-deliver. You really don't hear very much of us out in the industry in terms of these lofty goals with the chemical recycling, but we're quiet about it because we want to prove it and do it before we go out and make all these false promises. There's a lot of companies out there right now, it seems like they're out there for the cash grab, they're out there for the investment and not really delivering on their promises. There's a few pyrolysis companies that have made these massive investments and promises, and they're not up and operational as of yet. There are no commercial-sized pyrolysis facilities in the United States at this point. They're all demonstration plants. So we're working with a few key target offtake partners to help them get started with letters of intent, offtake agreements, etc. But yeah, that's our goal, 1 million tons. Rather lofty, and I'm really struggling trying to find the plastic that needs for our application. So enabling a lower carbon footprint with certified renewable chemicals. This is the mass balance. This is ISCC certification. So we can track it throughout the system. And if you're not familiar with mass balance, you probably use it yourself on a daily basis. There's a lot of utilities out there. You may have opted for windmill generated electricity, even though there's no windmill within 500 miles of you. So through a series of mass balance equations or logarithms, they're able to track the electrons that are being supplied to you. It's been done for many, many years in the pulp and paper industry, and now we're adopting it into the plastic industry. Without having the mass balance through the pyrolysis or the advanced chemical recycling technology, it probably wouldn't work. The economics are just not there. So by having this mass balance, it really works. So ISCC Plus certification is backward integrated into the entire system, right through generation of the PCR. And PCR can be post-industrial. The definition is it's at its end of its useful life. So helping balance emissions through value chain, carbon credits, and this is the whole mass balance concept that I talked about, to produce new products and to work directly with our customers. We have a number of select target customers that we're working with right now, as we have very limited amount of carbon credits that will be converted into polyethylene once our plant is up and operational sometime this summer. So Alliance Plastic Waste, we're one of the key founders of that organization. It's a 50-plus member nonprofit organization with a $1.5 billion investment into it, and it's really focused on trying to more effectively use the amounts of plastic that's out there and capture more efficiently what's out there. So what I've been focusing on trying to feed our waste plastic feedstock is the flexibles. I know MRFs and places like that really don't want the flexibles going in there. Well, we want them. And it's very key to our whole process in trying to get that cost-advantaged, sustainable waste plastic feedstock. So in partnerships, developing new electric cracking technology with Dow that I had mentioned, commercializing low carbon footprint technology for ethylene with Linde over in Germany, and accelerating plastic waste to chemicals technology. And we do have a joint venture in Europe with Blue Alp, and they are a chemical recycling company. We also have partnerships with a couple companies in the United States. And if you search our name and the name Nexus, you'll see us come up. And interestingly enough, I have to be back down in the south in a few weeks. We're a major sponsor of the New Orleans Jazz Festival, and we're going to be doing a pilot chemical recycling project with the waste plastic that's coming out of the New Orleans Jazz Festival. So I get to be at the festival for 2 weeks, which I kind of enjoy. So that's it for me. Thank you.
Great presentation, a lot of information, and it's great to see the large companies like Shell make such a commitment to the environmental stewardship and to this process that we're all going in together to find a use for just about everything. And Dan, that was a great presentation, and as he focused on getting the feedstock is so important and very hard to get that feedstock. I know one of the film plastics is one of the constant issues that we see. Many of the curbside collection systems don't take them. So I think that's an important place to begin. I know at my house we have the recycling bin that the city puts out, and there are certain things that go in there. Film plastics is not one of them. So I explained that to the manager at my house, and she said, we're going to find a place that takes film plastics. Sure enough, we separate them. She found a local store that takes the film plastics and then forwards them to an end user like a Shell. So it's good to have that type of environmental stewardship at the large company level like Shell and in the household. So thanks, Dan, for that great presentation. And thank you, Matt. Thanks, Gene, for running a great program. And I'll let Gene take it from here. Thanks.
Any other questions from the audience?
Oh, we got to do Q&A. We got Q&A on that notebook, not on this one. So Q&A. We're ready for Q&A.
I'm really not that familiar with the pyrolysis process, but why is it that you go the extra step to pelletize the material, the plastics, before they go into the pyrolysis process, and you do not pelletize the plastics that are going to be used as a feedstock going for recyclable products?
For that particular application, the density of the material mattered to that pyrolysis unit. We've created fluff for some pyrolysis units. This particular one, from a fluff that's 6 pounds per cubic foot to a pelletized material that's 20 pounds per cubic foot, their efficiency increased dramatically. So that was a requirement from them. And also we see it for logistics or shipping purposes in the pure fuel industry. So it's not a necessity. It's just going to be based on sort of the economics of whether it's logistics and shipping or the economics of the efficiency of the downstream equipment.
So you're just kind of densifying it a little bit for that.
That's correct. It's just a densified
why would you
product.
not do the same thing for the recyclable side of it, densifying it for shipping purposes as well?
They may require it, but in most cases, we're providing systems at the producer's facility. So we shred, create the flake, and then go directly into their wash line so they can start creating their widgets, their products right on site.
Thank you.
Yes, ma'am.
I can add to that as well. So what we're looking for is densified material, because we've identified 7 geographic locations around the United States where we want to aggregate waste plastic, but it's the transportation that's killing us. When you're dealing with 1.4 pounds per cubic foot of flexible film, we need it at 25 or more in order to be able to transport it around North America.
Question over here.
Yes, Matt. Just wondering if you guys been looking at carpet to be used for fuels?
We've done that as well. I just didn't use that as an application for this scenario. I wanted sort of you guys to see the exact same material used 3 different ways, but we've done carpet as well. Yes, sir. It's just it's a little more difficult in the sense of wear and the other materials involved with it, but it can create the same concept as an end product.
Okay, thank you.
Mm-hmm.
Michael has 1 billion pounds of carpet sitting in Dalton, Georgia. Would love to have
There's a
somebody
lot of
come
people in
take it off
Georgia
his
with a
hands.
lot of carpet. Yes, that is the carpet capital of the world for sure.
Yeah. And the challenge in the pyrolysis process, it needs polyethylene, polypropylene, and polystyrene. Anything that contains an oxygen, like PET, well, it's the absence of oxygen is what pyrolysis is, and unfortunately it doesn't work.
Go ahead.
Okay, yeah, this question's for Dan. And Dan, thanks for that outline. That was really nice to see from Shell. But a quick question. So the plant, if I heard correctly, the plant that you have in Pennsylvania is the largest polyethylene plant? Is it in the country or in the world?
It's the largest single construction site today in North America. At peak, we had about 9,000 contractors on site to build it. Total overall, it's going to produce 3.5 billion pounds of polyethylene split between multiple market segments, pipe, injection molding, blow molding, and about 1.5 or 2 billion pounds is destined for the film market.
Nice. And you mentioned, the feedstock I thought you mentioned was byproduct feedstock. I mean, what are you using? What was the feedstock that you were pulling?
Yeah,
in?
so
I know you had some recycled material, but then you also had some.
Yeah, so the Utica and Marcellus shale that's up in the Pennsylvania area is called wet gas, and wet gas means it has too much ethane in it, that it can't be sent directly to the consumer as natural gas, so it has to be removed. Historically, it would have been flared.
Okay. So you're basically using something that would have just been burned out.
Yeah, exactly. So we're recycling right to begin with.
Exactly. Okay. Well, that's very interesting, and that was really the basis of my question. I was just wondering where that was coming from, right? So having with the move to kind of go away from plastics, building the largest plant, but using, materials that would currently or be burned off with no value. I mean, that certainly seems like something.
And interestingly enough, North America has turned out to be the largest producer of polyethylene globally. Prior to that, about 10 years ago, they were looking at shutting down facilities. But with the discovery of gas and the ability to use gas in that process, it's brought us back to be probably 40% of all the polymer that's produced in North America is exported globally.
Any other questions for our panelists? All right, well, join me in giving them a round of applause. Appreciation.
And let's do this. Let's take a quick 15-minute break. We'll come back here at 10 o'clock and then run in through our last session. We're going to be
Recording
talking about
stopped.
solar panels.